Okay, folks, so going over the Unit 3 practice test. So real quick, for Unit 3, we've got three big different types of problems that we've got. And really, it's like two types of problems, and then type A and type B. So the first type are the relative motion ones. So with the relative motion, we've got something moving one way while being pushed another way. This plane's a relative motion problem because it's flying forward and being pushed backward at an angle. Now, what we're looking for here is we're trying to find the plane's velocity. First off, we got to go through and get what we have. So I'm going to call VP the plane velocity, so that is 180 meters per second, and then VW is going to be the wind velocity, which is 20 meters per second, but it's directed 210 degrees relative to the plane's motion. So plane's motion is 0 degrees, and then this is 210 degrees here. Now here's the thing. Ooh, geez, these are not to scale. If that's 20, that is definitely not 180, and vice versa. So I'm just gonna man, I don't know what dingbat did that. Stupid passed me. Anyways, so I've got 180 meters per second going in one way, and I'm adding a vector. So when we add vectors, we always add head to tail. So it's gonna look something like, no, it's not even gonna look like that. That is still way too long. But at least it's going to give me a better idea of what my resultant vector is going to be. So my resultant vector is going to be this green one here. So to find this resultant vector, well, we've added up vectors so many times. So we want to do VP in the x direction, which is going to be 180, whatever VP is, times the cosine of the angle that it's acting at. Well, the cosine is 0, which is 1. VPX is going to be 180 meters per second. VPY is going to be 180 sine 0 degrees, and that's going to be 0 meters per second. Okay. We do the same thing with the wind. We want to find the x and y component for the wind. So that would be 180 cosine of 210. Now, when we do that, so I did not do this ahead of time. I get a negative 155. Oh wait, oh my goodness. You can tell I'm not doing it ahead of time because I'm messing up. That should be a 20 there. Man, I hope you did not pause and send me an angry email in the interim time. Anyways, you're going to get a negative 17.3 meters per second. And then in the y direction, well, you're going to do the sine of, so it would be 20 sine 210, which is going to be negative 10 meters per second. So now we have a much more manageable system to work with here. We've got a vector that's 180 meters per second forwards. We've got another one that is back 17.3 meters per second-ish. And then we've got another one that is going down 10 meters per second. So we're looking to find that. So these two, 180 plus 17, or negative 17.3, is going to get me 162. So V total in the x direction is going to be 162.7 meters per second. And then Vy is going to be 0 plus negative 10. So I'm going to square 162.7 and add 10 squared, which is 100, and then take the square root of that, and I get a velocity of 163 meters per second, which makes sense. It's moving forward, but it's getting blown back into the side. So now we want to find the direction of the plane's velocity vector. So we want to find, really what's going on is we want to find this angle right here. So that angle, we can figure out the tangent of that angle is going to be y over x. So we take Vy, which is negative 10. Divided by 163. And then I take the inverse tangent of that, and I get my angle is going to be negative 3.51 degrees. Usually we would want to represent that in a regular circle, so we would add 360 to that, and it would be 356.5 degrees. But seriously, 6 one, half dozen the other, as far as I'm concerned there. What direction should the pilot turn the plane in order to fly forward? So if he wants to travel just east, 0 degrees, what direction should he turn? Well, he should turn to, if this is negative 3.51, he should move to 3.51. That would even it out. Okay. So, number two. Number two is a horizontal projectile problem. So, a horizontal projectile problem, we have an initial velocity that is entirely horizontal. So the nice thing about these is no matter what the initial velocity is, all things are going to fall the same distance in the same amount of time. So if the candy bars fall, oh wait, we gotta draw the acceleration vectors. So the acceleration vector is the same at all points. It would be like that. Oop, there we go. So it's AY, AY, AY. If we wanted to do the velocity vectors, it doesn't ask us to do this, but I can do what I want on my own test. So the velocity vectors are going to point like that, and they're going to get longer because you speed up as you fall down. That's why it's okay to fall off your bed. It's not okay to fall off a cliff. At least I assume so. Who've never fallen off a cliff, personally. Okay, so for this one, we know the distance that these candy bars are falling. Find the amount of time it takes for them to land. Oh, hey, V naught Y, since it's horizontal, is going to be 0 meters per second. If I'm moving horizontally, I'm not moving in the Y direction at all. So now I can use my how far formula. Y is equal to Y naught plus V naught Y T plus 1/2 G T squared. Oh, hey, you guys are getting the green sheets tomorrow, so they're hot off the laminator as we speak. So I want to solve this for T. We could plug it into the quadratic formula, but we don't have to because that's going to go away. That's going to go away. And we're going to be left with negative 0.55. So I'm just plugging in for Y naught is equal to 1/2 of G is negative 4.9 T squared. So T is going to be equal to 0.55 all over 4.9. Square root the whole thing, and you should get about 1/3 of a second. So to find the candy bar's horizontal velocity when it hits the ground, Well, we use our Vx formula. Vx is equal to V naught x. There's no horizontal acceleration, so whatever it's launched at is the horizontal velocity that it lands at. The candy bar's vertical velocity upon impact is going to change, but we're going to use the same formula, just this time for the y direction. So Vy is equal to V naught y, how fast we're going initially, 0, plus negative 9.8, our acceleration, times how long we've been falling for. So if the candy bar falls for 0.33 seconds, then that is going to be 0.33 times negative 9.8, and we get negative 3.23 meters per second. Okay. How far does the candy bar travel horizontally before landing? So, in the x direction, to find the range, whatever the horizontal velocity is initially times the time of flight is going to be how far it goes. So that is going to be 1.4, our initial velocity, times 0.33. And we get it goes about 46 centimeters. Oh, no, you know what? Maybe when you work this out, maybe you got something a little different, like 4.64, whatever. On the test, if we are off by a small amount, a couple percent, I'm not going to sweat it. Honestly, if you were able to guess 0.46, good for you. But honestly, if you guys actually want to get points on these tests, you should be working out as much of the problem as you can so that I can give you credit for the error carries through once. Oh, hey, the machine starts making king-size bars, double the mass. Double the mass. Where should the bin be placed to catch the king-size bars? At 0.46 meters, because it doesn't matter how heavy the king-size bars are, they're not going to fall down faster. Everything drops at the same time, right? If I'm dropping two things that have two different masses, they always land same time. Anyways, so going on to the back, there's a last one here. Oh, what that dingle? I bled through. So these last two are projectiles at an angle. These are the problems that if you can do something like this, you know what, you're going to be fine. You're going to be fine. So we already worked out this top one in class. I'm not going to rehash that. So this one, the golfer is hitting the ball at 45 degrees, and then the ball lands on an elevated green. So it's going to look something more like this. So we got a 45-degree angle there, and then we land 0.27 meters above zero. So to find when the ball lands, just like how up here we solved for y, we're going to do the exact same thing, except now our final y isn't 0, it's going to be 2.7. So our final y is 2.7 meters. And then we got to recalculate what this is going to be. So I should probably find my v naught x and my v naught y originally, just to get that out of the way. So 22.3, and then it's going to be, for v naught x, it's going to be the cosine of 45. Now, just because I know this, at 45 degrees, sine and cosine equal out. So I can just go ahead and write the same thing for my v naught in the y direction. And that's going to save me, I don't know, a smidge of time. Anyways, so now I've got y is equal to 0. Well, actually, y isn't going to be y. It's going to be 2.7 if I'm plugging everything in, plus 15.77 times t, plus 1/2 gt squared. Now, at this point in time, I want to move that 2.7 over here, so I got a negative 2.7 plus 15.77 t minus 4.9 t squared. If I'm plugging this in as a quadratic, that's a, that's b, and that's c. So now I need to write out my quadratic formula. Oh my goodness, I'm going to go over and get a green sheet. So looking at my green sheet, I've got negative b plus or minus b squared over minus 4ac over 2a. So I can plug this stuff in. So my time is going to be negative 15.77 plus or minus the square root of 15.77 squared minus 4 times 4.9. Oh, negative 4.9. Well, okay. 4.9 times negative 2.7, those are going to cancel out. Yeesh, I don't have enough room there. All over 2 times negative 4.9. So, now, I dropped my fancy calculator. And I don't have it anymore. So I'm just going to do this out piecewise. So I've got 2.48.7 minus 4 times 4.9 times 2.7 gets me 52.92 all over negative 9.8. Taking my square root up top, I've got negative 1577 plus or minus 13.99 all over negative 9.8. Just on a hunch, I'm going to do the negative first because I feel like I'm going to want a larger time here. So that would get me 15.77 plus 13.99 divided by 9.8 gets me a time of 3 seconds. And 3 seconds seems like a rightish amount of time for a golf ball to fly to the green. Okay, what is the ball's range? So to find the range, that's going to be x is equal to v naught x times t, so 15.77. So roughly I'm going to get about 45 meters for this one. So 47.9 meters is how far this second one goes. What is the total velocity of the ball as it lands? Oh, hey, as the ball lands, it's going to have a velocity. Yeah. That velocity is going to have two components. Shouldn't be a surprise. It's going to be Vx, and it's going to be Vy. So we want to find what Vy is as it lands. So Vy is going to be V naught y plus g times t. So Vy is equal to 15.77 minus negative 9.8 times 3.03. And I get an answer of it is falling downward now at negative 3.9 meters per second. Fun fact, if it wasn't landing on this elevated green, if it was a flat surface, it should land at the same speed, right? But it doesn't. It lands at that speed. So now we've got to do, so V is going to be the Pythagorean theorem of those two. So 13.9 plus 15.77 squared. And then we square root that, and we get it's landing at a velocity of 21 meters per second. Okie dokes.